Hello, I'm Ian Roche, and today I will be giving a presentation on residuals. So first off, what is a residual? A residual is the observed value minus the predicted value. So mathematically, E equals Y minus Y hat, with E the residual, Y the observed value, and Y hat the predicted value. If you look at the graph, the vertical lines connecting the data points to the prediction line are the residual values. Next, we will be looking at a few of the common plots used with residuals. So this first plot is just a normal plot between residuals on the y-axis and the independent variable on the x-axis. And you can look at this plot and see if there's any patterns to determine if your model is good. The next plot is a sequence plot, which is used if your data was collected in a certain sequence in order to determine if the sequence had any impact on the data. The third plot is a box plot, which is used to determine, first off, the second quartile, which begins there, the third quartile, which begins there, and the mean, which is there. The third plot is a normal probability plot, which is used to see if your data is normally distributed. And on the x-axis, you have the expected value, and on the y-axis, you have the residual value. And if these two values are closely correlated, in other words, it makes a diagonal line, then you can reasonably assume that there is normal distribution with your model. Next, we will be looking at a few of the properties of residuals. The first property is that the sum of the values of all of the residuals will ultimately equal 0. That's to say that this value, which is negative, plus these values and these values, which are positive, will ultimately give you the value of 0. The next property is that the average of all of the residuals will equal 0 as well. Again, this is because some of the values are negative and some of the values are positive, and when you average them together, you will always get the result of 0. Next, we will be looking at a few plots with a good linear regression that fits the data. In this first plot, it is a normal scatter plot of the data, and you can see that the regression line right here goes through the middle of the data, and there are no apparent patterns that throw off the line. This next plot is the plot of the residuals, and you'll notice that the residuals are evenly distributed on both sides of the line, and the red trend line goes almost exactly with the expected line, apart from at the end here, where a few of these points are skewing the model. So what important information can we get from residuals? First, that the regression function is not linear, that the error terms do not have consistent variance, that the error terms are not independent, that the model fits all but one or a few outlier observations, that the error terms are not normally distributed, and that one or several important predictor variables have been omitted from the model. So, how can we use residuals to tell if the regression function is not linear? In the first graph, you can see the original regression. And if you look closely, you can see that it begins increasing by a lot and slowly becomes less and less. While you can tell this from the original graph, it is not super apparent. In the residual plot, on the other hand, it is clear that all of the points are not random. It makes an upside down U shape, which is a clear signal that maybe we should change our model and use something other than linear regression. Next, how can we use residuals to tell that the error terms do not have consistent variance? Variance is the distance between the expected value and the residuals. And with consistent variance, we would expect to see all of the points to fit between horizontal lines without outliers around other areas. It's clear in the first graph that this begins small, but then increases with age. From that, we can see that the variance is not consistent. On the second graph, it's even easier to see because if variance was consistent, all of the points would be below one line that goes horizontally. Instead, we can see a sharp increase as time goes on. From this, you know that your model does not have consistent variance. The Brown-Forsyth test is a test used to determine whether error terms have consistent variance. In the test, the residuals are divided into two groups. Each group contains about the same number of variables, with one having comparatively smaller and one comparatively larger x values. Next, a calculation is carried out which will determine a p-value. And according to that p-value, we will either accept or reject a null hypothesis. The null hypothesis in this case is that there is no variance between the two groups. The alternative hypothesis is that there is variance between the two groups. If the resulting p-value is above the designated significant amount, the null hypothesis is accepted, and we assume that there is no variance between the groups. If the p-value is below that amount, the null hypothesis is rejected, and we assume that there is variance. On the graph, this would look like a division with half of the values on the left and half of the values on the right, and the null hypothesis would be showing that the variance would be equal. In this case, however, the p-value that would come out would show that there is variance between the groups, and we would reject the null hypothesis. In a linear regression model, it is important that the error terms are independent. Residuals can be used to test whether or not this is true. When data is obtained in a sequence, it is important to compare the residuals to the order in which that data was obtained. In the first graph, we can see that there is a direct linear relationship between the residuals and the time order of the weld. In the second graph, we can see a different pattern that indicates that time order has some effect on the data. In this case, it would be important to change our model to show each of these effects. In this way, the model would come out more accurate and give us better results. In order for a linear regression model to accurately predict the real-world results, it is important that the model fits the data. Outliers can skew the model away from the real world. By using residuals, we can see if there is data that is skewing our model. In this case, this point is 6 standard deviations away from the normal data. This outlier would cause a normal linear regression line to be skewed and inaccurately predict the real world. In the next plot, we can see an outlier here, and in the residual plot, there is a strange pattern of the residuals having a linear downward slope. This is because the linear regression is skewed towards the outlier. If we were to remove the outlier, the linear regression would follow the data and accurately predict. In other words, if this point was not there, these data points would skew this way, and there would be accurate prediction in the model. In order for a linear regression model to accurately predict, the error terms need to be normally distributed. This can be checked through the use of a normal probability plot. In this plot, you can see that the x-axis are the theoretical quantities, and the y-axis is the residual. What you would want to see for normally distributed data would be a linear line that correlates to the theoretical quantities. In the right plot, you can see that it is not normally distributed here and here. This would cause errors in the final model. Here are some more examples of graphs that do not show normal distribution. On the left, we have a model that is skewed right. And on the middle, we have a model that is skewed left. The final one shows a model with heavy tails, but that is symmetrical. All of these point to non-normally distributed errors. The final thing that residuals can help us to see is when one or several important predictor variables have been omitted from the model. It is important to plot residuals against variables that were omitted from the model in order to see if they should be added to improve the model. In these graphs, you can see originally the linear regression used both machines at the same time. This regression looks good, and the data points don't show any patterns. But when you add the omitted variables, that they can be separated into company A machines and company B machines, you can see that with company A machines, the model underpredicts and there is a bias. With company B machines, the model overpredicts and gives an upward bias. The model could be improved if the company's machine was added as a variable. That concludes my presentation on residuals. Thank you for listening.